Jai Hind everyone. Myself, Mrignainy Kansal, Assistant Professor in the IT department, will going to discuss about the complexity measure. In this video lecture, we will going to discuss the topic how to calculate the complexity measure in the software engineering. First of all, what is actually a complexity measure? Why it actually required to do so? How to modularize a software system so the resulting modules are both testable and the maintainable. So the currently is to limit the program by their physical size. That means if I want to measure the complexity of a program, that means we are trying to what? We are trying to calculate the line of code. The number of lines will be occupied in a particular program. But if we want to decrease the complexity, what we are doing? We are just reducing the size of the code. That means we are just reducing the size of the line of code in the program. So currently is to limit the program by the physical size and not adequate. 50 lines program consists of 25 consecutives if, then and construct. So these are we are trying to just reduce the line of code with the help of just making it in a submerge in a single line and try to reduce the complexity by we are calculating the complexity measure on the basis of the line of code. Now, what the complexity measure is? A measure and control the number of paths through a program. That means we are trying to control the number of paths through the help of the program. Path, what is the path is? The way through which we can execute the program is known as a path. And measure is to calculate the measure the way we are actually doing the single program in a multiple ways. So the cyclomatic complexity number, which is represented by the Vg of a graph G with the vertices E, edges and vertices, and the P number of connected component will be there in the graph. That means here we are having the cyclometric complexity, which is represented by the Vg and which having three different components, three different variables used. First of all, n, which is representing the vertices. Next is the edge of the graph and the connected component. The graph which is having a region inside the graph. The formula will be defined by the Vg. That means we having E, that means number of edges in a graph minus n number of vertices plus 2p. So this is our what? Formula will going to be used while we are going to be calculate the cyclometric complexity. So the first theorem which says why the cyclometric complexity is in a strongly connected graph G. That means here we are actually calculating the cyclometric complexity with the help of the graph. First of all, we need to convert the line of code into the graph, the way they are connected. What is a graph? Graph is representation by the help of the vertices and the edges. So the graph is represented by G. The cyclometric number is equivalent to the maximum number of linearly independent circuit within G. This is the first theorem which will going to be explained that how we will going to be calculate the cyclometric complexity. So the cyclometric complexity very easily and defining by the help of the graph, that first of all you will going to convert the line of codes into the graph, and the graph is a representation of the number of edges and the number of vertices. And the cyclometric complexity will directly linked or directly equivalent to the linear independent in the circuit, the maximum number of linearly independent in the circuit. Given a program, we will going to associate with a direct graph that has a unique entry and the exit node. That means in a single program, we will going to convert them into the graph, and that graph will associated with a direct graph that has a unique entry and a unique exit, as like we having a unique entry within the graph in this way. There is a unique entry into the graph, and this is the exit. This is the entry and this is the exit. So the unique entry from the above part of the node of a graph, and the exit is at the end of the graph. So each node in the graph corresponds to the block of code in the program. Every node here will representing the line of code within a program. That means each and every line is going to be converted into the every node in a graph, where the flow is a sequence and the arc respond to the branches taken to the program. The flow will represent you the complete sequence how the program is going to be evaluated, and this arrow, this arc will going to be represented that in what direction the line of code will going to be executed one by one. As we can see that in this node, let's suppose I'm taking it as a number A. A will reach to B directly, but B will going to reach to C with the help of either in a D mode or in the E mode. So there are two options. Either B will move to the D or move to the E while reaching to the C, the exit node. So this graph will showing the relationship between the lines of code among them with the help of the arc. Either they can directly move to the another part or how they will reach to the end of the program. Known as the program control graph. This complete graph is known as what? This complete graph is known as the program control graph. This is the complete graph. Program control graph is just the representation of the line of code into the graphical way, which are containing the number of nodes, that is n, and a vertex, n edges, that is e. Now, the complexity measure. The complexity measure will be going to explain how we will going to be convert each and every line of code into the graphical. This is a notation of the graph G. Every node will going to represent you the line of code in a program. First of all, we having this node. This node represent what? The each and every line of node in a program. I can move with the node A to the any of the node, either B, either C or D. That means there is a first initialization of the program in a line of code which initialize the program, and then after initialization we have the condition, either we can move to the B or to the C or to the D. That is the choice will given provided to the user. Once we will move to B, okay, then B will move to the C only, E, and E either move back to the B or move back to the A. That will be the back condition which will make it to the initial state, or it will be come up to the end of the program. This is the end of the program. This is the start of the program. Okay. So this is the way we are representing the every line of code in a program with the help of the graphical representation, that we are moving from here and reaching either B or E, A or F. This is the first node if I am taking the first choice as a B. Now, for the second choice, if I am taking A to the C, then what will going to happen? If I choose this, what will going to be happening? C will reach to the F directly. There is no other node or no other alternative. If I once reach to the C, it will directly reach to the F. There is no other alternative after the C will going to be repeat, or there will be no back loop which will reach back to the initial stage. Now, if I choose the D, then how it will going to happen? If I choose D, this, then with D, we can only move back to the C, and the C then move back to the F. There is a dependency of D over the C. If once you reach to the D, then you have to back to the C, and then it will be come to the end. So this will represent you the complete way of representing the line of code in a program into the graphical mode. Next. Now, from the graph, the maximum number of linearly independent circuit in G is given by this. How this will happening? The number of nodes in the graph, how much the number of nodes are? That means A, B, C, D, E, F. 1, 2, 3, 4, 5, 6. There are number of nodes. Nodes will be equivalent to 6. Edges 1, 2, 3, 4. The edge will be represented by that is 1, 2, 3, 4, 5, 6, 7, 8 and 9. So these are the edges are 9. There are 9 edges. And what else we left with? The connected component, matlab region within the circuit. There is a loop here. There is a region created here. This is the one region. This is another region within what? Within the graph. This is the region created in the graph. Then when we are moving and calculating here from the above previous one, the number of edges, this formula will be equivalent to what? E minus n plus 2p. Is that clear? E. What is E? E will be represented as 9. N will be represented as 6. That is 9 minus 6 plus P. The component will be connected as there is a single graph in the representation will be this. There is no different graphs are there. There is no disconnected graph in this. So there is only one graph. So the P value of P will be equivalent to what? 1. So the resultant will be 9 minus 6 plus 2. That is 5. So we receive that could choose the 5 independent circuit from the G. The circuit having the 5 independent A, B, E, F. What is this? A, B, E, F. Now we come up with the A, B, E, F. A, B, E and F. This is the first independent path we choose. Okay. Now next is B, E, B. That is the circuit. Here B, E and B. Then next is A, B, E, A. Here is A, B, E and A. This is another path. Okay. Now A, C, F, A. Where it is? A, C, F and we are reaching to the A back. Now A, D, C, F, A. A, D, C, F, A. So these are the 5 different independent paths we are getting from this graph G. Now the several properties of the cyclomatic complexity that the vertices in the G must be greater than equal to 1 and G vertices is the maximum number of linearly independent path in G. It is the size of the basic set. This is a condition within the cyclomatic complexity. Inserting or deleting the functional statement to G does not affect the VG. And G has only one path if and only if there is only one node in a graph. If there is one node in a graph, that means there is only one path in a graph. That is represented by the cyclomatic complexity. These are the 4 different terms and the 4 different properties in the cyclomatic complexity. Now, inserting a new edge in a graph will increase the V, the unit by unit. You add one node, one edge will also increase one node also in the graph. G depend only on the decision structure of G. The decision taken by the G will be dependent on the decision taken by G. This is the decomposition, as we get to know that this is the formula for the calculating of cyclomatic complexity, number of edges minus vertices plus 2p. So what is P is? P is the number of connected components. So all control graph will have only one connected component is defined here. So in the previous slide, as I said, that we will going to be take 1 as a connected component is because there is no 2 different disconnected graph. There is only one single connected graph. That's why the value of the P, that means all the control graph will always have the value of P is equivalent to 1. Now the next example is what? We having the graph M. M graph is representing having what? This graph is how much? The number of nodes, that means n equivalent to 4 and edges are 3. For the graph that is known as the A. A is also having number of nodes equivalent to 4. And the edges are how much? is also 4. Next, we have this B. This graph B having the number of nodes equivalent to 5 and the edges are 6. This is the all calculation we are doing with the help of the decomposition of the graph M, A and B. And every graph having a different values of their number of edges and a number of nodes. Now, since we having 3 different disconnected graphs, so the value of P will be considered as 3 because there is not only single graph, we decompose the graph into 3 different components. So, the connected components are also 3. So, we calculate the complexity with the help of what? We are doing complexity of M, complexity of A and B. And union of all these will give us the number of vertices in this, complexity in this. The complexity formula is this. If we are doing the what? We are just making the union of all the complexity, do it with the union and calculate as this. Either you notice like this, or you may also perform the number of we can do the calculation of the cyclomatic complexity of M, then for A, then for B. So how you will going to be calculated? As you know that it is 4, 3. That means here it will be what? It will be 3 minus 4 plus 1. How much it will be? It will be going to be 0. That's how you will going to calculate each and every complexity like this and like this. And the sum of sum will be 6. This is the complete control graph complexity in this program. Now, the simplification. How the simplification will going to be performed. There are 2 ways to perform the simplification. Allow the complexity calculation to be done in term of the program. Syntactic constructs. Calculate from the graph from. How? First way is the cyclomatic complexity of the structured program is equal to the number of predicted plus 1. The number of predicted value plus 1 will going to the first way of calculating the cyclomatic complexity. How? That is, we having this graph G, and with the graph G, we are defining the complete flow. The flow having nodes and the edges in this, and the graph starts from here and end maybe here or maybe here. There are 2 ends. The start may be 1, the end may be 2. So, with the help of the simplification, what we will going to perform? We will do first from the graph, we will calculate the connected components with the 3 values. Pi. Pi is what we first calculate is the equivalent to the number of predicted plus 1. So, the value of pi plus 1, the predicted value is 3 plus 1, 4. This is a cyclomatic direct formula with the help of the predicted number of values. The second way is from the help of the Euler formula. The Euler formula, what does it say? G is a connected plan graph with n vertices, with E edges and the R regions. So, with the help of the number of regions, how we will going to be calculate this? So, n vertices, E edges plus R region will be equivalent to 2. So, number of region will be equivalent to the cyclomatic complexity. The number of region you will going to be calculated from here. That means the value of R will going to be equivalent to same as the complexity value. How it will be done? It will be same as this. If I am taking this equation, that means n minus E plus R equivalent to 2. Recalculated. That means this will give you the value of the complexity. How you will calculate this? R will be equivalent to what? Is E will move here, N will be over. So, E minus N plus 2. What you have find the same formula as we have discussed previously also, that V of G will be equivalent to E minus N plus 2P, where the value of P will always be 1 because of the regular flow graph, control flow graph. So, this is the simplified formula. Either you can calculate in the term of the region or you can calculate directly from here. This is the graph which will define you the number of region. Number of region is a circuit within a graph. How? Either you can calculate it by this or you may calculate it by the another way. This is simplest way. Suppose if I want to calculate then with the formula of V of G equivalent to E minus N plus 2P. The number of nodes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So N equals to 10. Edges 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Equivalent to 13. And how the formula is 13 minus 10 plus 2. It will be same as 5. First method which we have discussed in the previous slide is this. And the second is with the help of the number of region, that means the number of circuit involved in a particular graph. This is the outer region which will be considered as 1. Then this is the another region, this is the another circuit, this is another circuit, and this is another circuit. That's why there are 4 plus 1. The pi value within the graph plus 1 will be equivalent to the 5. That shows the what? That shows the complexity value will be calculated with the help of the number of region. So the non-structured program, there are 4 control structure to generate all the non-structured program. 4 different control structure to be help in generating this. What are those? That is the first non-structured program is. This will show the non-structured way of programming that where we having 2 different end. Start will be same, but the end is differ. The end will having the 2 different outputs, but the start will be same. So this will also a program which is non-structured but helping in calculating the complexity. This is the another way where are 2 different start. Either it starts from here or from here, but the end will be 1. 2 starts with a single end and 1 start with 2 ends will be defining the non-structured program. Now the next one is where is the interlinked between the nodes and having 2 starts. Here it will be start or here it will be start. The end will be here. Here we having 1 start with 2 end. The end node are 2 different. So this is the start and start and end. The result, a necessary and a sufficient condition that our program is structured is that it contains a subgraph either A, B or C. A non-structured program cannot be just a little non-structured. That is not a non-structured program must contain a list of the graph A to Z. At least they are containing any one from A to Z. Case first. E is before the loop. E is on the path from the entry of the loop so that the program must have the graph as follows. E is before the loop. E is on the path of entry of the loop and so the must graph follow this step completely. So this is on the basis of the case that is E must be before the loop to be performed. Next is E is after the loop. How? E is after the loop will control the graph who will appear at first. Next, E is independent of the loop. The graph C must now be present with. If there is another part that can go to the node after the loop E, then D will be the graph generated by this. This is the complete notation will be explained here that there are different cases on the basis of the given graphs. The result read. A necessary condition and a sufficient condition for a program to be non-structured. So these are the 4 different conditions to be program having the non-structured form of way. The cyclometric complexity of the non-structured program is at least 3. At least there must be the value of 3. Less than 3 is not the cyclometric complexity for the non-structured program. For the result 5, this will be having not branching out the loop as per the decision of A to C. For the structured program can be written not branching the decision on the basis of B to D. And last, the structured program is the reducible process of the removing subgraph with the unique entry and exit of the program for the unit complexity. The non-structured program is having M be the number of proper subgraphs out of the single graph. And the definition is given by the help of this, where V will going to be represented the number of node or of vertices, and E will represent the what is the edges. The essential complexity of the structured program is always 1. The testing methodology, let a program P has been written, its complexity V has been calculated, and the number of part tested is actually complex. So there is more testing to be performed. The program flow can be reduced in a complexity by V of AC to be taken out, and the portion of the program to be reduced by the help of line of code. Suppose that A, C equivalent to 2 and the 2 tested paths, this will be done and cannot be executed. So this is the graph will represented the testing way of performing, that how we will going to be reduce the value so that the complexity get reduces. So we having the AC is less than C in the case of 2 holes, and if it is equivalent to V, then the new complexity will be the less than the previous one. So this methodology will be noted as V is the only minimum number of independent path, and it should be procedure with no proper guarantee of the proper software and improving the quality of the software.